Well, hey everyone, hope you're having a great day. Welcome back to the channel. What we're going to do is spend a little time today talking about the time value of money. We're going to cover the present value and future value functions within Excel. Also, we're going to look at the payment function, and we're going to take a few minutes to look at the net present value function. So let's just get right into it. So before we actually get into Excel and talk about the functions that are built into Excel for time value, let's spend just a moment talking about the concept behind time value of money. The basic primary concept is that money today is worth more than the same amount of money in the future. In other words, you could buy a certain amount with $100 today. 10 years from now, $100 won't buy nearly as much as that will buy today. So money grows over time, and that growth of money we refer to as the rate of interest. So let's see how that works. So if I invest $100 today in the bank at 5%, and I leave it there for 1 year, how much will I have at the end of 1 year? It's a pretty simple computation. We're simply going to take the $100, add 5% to it, and we're going to get $105. So how much would we have at the end of 2 years? Well, it's not going to be 110 because in addition to the extra $5 we're going to earn in year 2 on the original 100, now we're going to be earning interest on last year's interest. So it ends up looking something like this, and we end up having about $110.25 at the end of year 2. We can go to year 3 and we get a similar situation. At the end of year 3, we're earning another 5% interest on the 100, but now we're earning interest on year 2's interest. We're also earning additional interest on year 1's interest and interest on the interest that we earned last year from year 1. So it starts to grow, and we end up with something that looks like this, $115.7625. Now, that doesn't seem like a lot of difference, but it is, and it compounds over time. Now, we can take this out 20 years, 30 years, 40 years, but the reality is the basic formula simplifies down to this, that the future value of anything is the current present value of that amount times what we call a future value factor. That factor is based on the interest rate and the number of periods. Now, we put that together in this formula, 1 plus the interest rate raised to the number of periods. And it turns out that when we multiply that times the present value, we will always get the right future value amount. So when you use the future value function in Excel, it's using this mathematical function underlying that computation, and this is what it's giving you. Now, we also have something called present value, which is simply the reverse of the future value. So we know what the amount is in the future. What we don't know is what the amount is in the present, the equal amount. So we're going to discount that future amount back to the present, and we do that using a similar formula. This time we're going to say the present value is equal to whatever that future value amount is multiplied by 1 over the future value factor, or the inverse of that factor. And that will give us the present value. It'll discount that back. This is really nothing more than an algebraic manipulation of the original equation. We put, instead of having future value by itself on one side and future value on the right side, we're now going to put present value on the left side of the equation and move future value to the right side of the equation, and we end up with this formula. Now, let's give an example. Let's say we have $1 million, or we want to have $1 million when we retire in 45 years, and we're going to invest that at 5%. So what is the present amount we would need to put away so that if we left it for 45 years, it would grow to $1 million? It turns out that that amount is $111,296. Well, I don't know about you, but I don't have that. So we have a concept we're going to also look at called an annuity concept. So the future value of an annuity basically says that we're going to invest a stream of equal payments over time. This is what we call compounding. Okay, not only are we going to earn interest on interest, but now we're going to be adding to the base each year too. So it's also going to be growing. So the future value of annuity is the future value of a stream of equal payments made at the end of each investment period at a given interest rate, an average interest rate. We're going to make a couple of assumptions. All of our payments will be the same, and the interest rate will stay constant over the period. And we know that's not real, that doesn't happen in real life, but that's okay. That's why we have to continue to make investment decisions over our lifetime. Now, if it turns out if that payment is made at the end of a period, we call that an annuity. If it's made at the beginning of the period, it's called an annuity due, and that's what we see most often in the computations. Now remember, most of us don't have that $111,296 just plop down in the bank today and leave it, unless you happen to have an inheritance. But you don't have that. But what we can do is we make a little bit of payment along the way, and it turns out that that's much easier for us to do to accomplish the same goal. Now, so let's look at a simple example. So if I invest $100 today at an interest rate of 5% and I leave it for 1 year, same computation as we had for regular future value, which is excuse me, let me back up. It is it's not gonna let me back up, but it's 1 plus 5%, right? So if we leave for the second year, not only are we going to add 5%, but we're going to add another 100 to it. So we see that the total at the end of 2 years is $215.25. Now, as it turns out, the formula for that is pretty complex, but it simplifies down to this. The future value of an annuity due is whatever the payment is times 1 plus the interest rate times 1 plus the interest rate raised to the n minus 1 divided by I. It's really complex, but that's what it actually simplifies down to. The payment feature or function within Excel utilizes and exploits this particular formula. So thank goodness we have Excel, right? Now there's also a present value of the annuity due. We can do that backwards as well, and that it's not simply the inverse of the future value of an annuity due function. It's a little bit different computation, and this is the formula. But again, the annuity function within Excel exploits this equation. So now that we're sort of familiar with that, let's go look at how those functions actually work in Excel. So Excel has several functions built into it that allow us to do these time value computations. So the first one we are going to look at is the future value function, which is FV is the function. So I've got 3 cases here we're going to look at. In the first case, we have $100,000 now. We're going to invest it for 25 years at 4.2%. So what will it be worth in 25 years? So we'll start down here in cell B7, and I'll start with equals FV because we're looking for the future value, and I would do Control A to bring up my dialog box. I'm going to move that over here so we can use it. First thing it asks for is the interest rate, and that's going to be right here in cell B5. Then the next thing it looks for is the number of periods, and that's going to be down here in cell B6. I don't have a payment in this problem, but I do have a present value. Now, what's interesting about this function, it allows you, particularly if you use this dialog box, it allows you to dictate what your computation is going to be based on which input you identify. Excel knows that since I did not identify a payment, that this is a simple future value problem, and it will use that simple future value function that I showed you earlier. So when I hit OK, it's going to compute the future value, and it is $279,700.33. You now notice that it gives you a negative number here. It's kind of a quirk of future value that it does that. You can change that if you want to by simply putting a minus sign in front of the future value if this negative thing bothers you, and that makes it into a positive number, but it's still the same amount. It's just sort of a quirk of Excel. Now, I kind of prefer it as a positive number. I think I know whether or not it's coming in or going out, but Excel doesn't, so it assumes this is going out. But so I always put the minus sign in front of it. Now in the second case, we don't have a present value, but we are going to make annual payments of $24,000 for the next 25 years at 4.2%. So what is that? How does that work? Well, we're going to do the same thing, equals future value, Control A, bring up our dialog box, and it asks us for the same information. We're going to identify the rate, which is 4.2% in cell C5. The number of periods is in cell C6. Then what we've got is the number of payments, which is up here in cell C3. We don't have a present value, so all we have to do is hit OK, and it's going to give us our future value of those payments. Now, I'm going to put a minus sign in front of that again. And it turns out that if we invest $24,000 a year for 25 years at 4.2%, we will have $1 million. Now, that's about $12,000, or excuse me, $2,000 a month. That's going to be about $500 a week. I don't know if you could do that. Maybe that's not reasonable. Maybe you could do $1,000 a month. So that's $12,000 a year. That's only going to get you $513,000. Though if you could earn 6%, it's going to get you a whole lot closer, right? And if you did it for 35 years instead of 25 years, you're going to get easily to $1 million, even if you only have 4%. Well, let's say 4.5%. Whoops. Well, I'll get there in a minute. 4.5% for 35 years, and that's $977,000. So that would work. That's $1,000 a month. A lot of people can do $1,000 a month for 35 years. It does tell you that extra 10 years gets you an extra. Whoops. That extra 10 years gets you an extra $430,000 for almost $440,000, really. So it's a tremendous amount going an extra 10 years. So the earlier you get started, the better you're going to be. Now, in this last case, we've actually got two things. We've got $100,000 present value we're going to invest, and then we're going to invest $12,000 a year at 25 years for 4.2%. And in this case, we'll actually use all of the features of the future value function. We're going to put in the rate at 4.2%, which is in cell D5. We'll put in the number of periods in cell D6, and we'll put in the payment in cell D3, and we'll put in the present value in cell D2, and it'll compute all of that for us and adds up to $546,000. Again, I didn't put the minus sign in front. So there we go. So if we had 4.2% for 25 years, we have $513,429. If you add $100,000 at the beginning, you're going to get $546,000, and that'll be your. That doesn't actually look right to me, and I don't think it is. Let me go back and look at this again. I've got my rate, my interest rate, my payment, which is here, and my present value, which is there. There we go. Now I've got it right, and it gives me $793,129 because, and basically in this case, it's the sum of these two amounts right here, but it adds them all in one function. So if we go to present value, we can do a very similar kind of thing. We've got 5 cases here we're going to look at. In the first one, we know we want $1 million in the future. We're going to invest. We want to invest a certain amount, an unknown amount, for 45 years at 5%. So we'll do present value function. Works just like future value equals PV. Control A for our dialog box. We're going to put in the interest rate. We're going to put in the number of periods. We're going to put in the pay. We don't know the pay. There is no payment. And we'll just put in the future value, and we'll hit OK, and we get a future value of $111,000. Excuse me, a present value of $111,000. Is if we put $111,000 in today, we'll have $1 million in 45 years. That's the problem we worked out earlier. So in the second case, we're going to invest $50,000 a year for 20 years at 6%. So what do we get there? Same thing, equals PV, Control A for our dialog box. Our interest rate is going to be 6%. Our number of periods is 20. Our payment is 50. There is no future value. We just hit OK. And we end up with, again, I keep forgetting to put the minus sign in there, $573,496 if we invest $50,000 for 20 years at 6%. So that's the present value of that. The present value is that. So if we invest, so the equal, this would be like the lottery, right? If you win $1 million in the lottery, you're not going to actually get a $1 million lump sum. They're going to give you $50,000 a year for 20 years. So how much of a lump sum payment would you get if you decide to take it all up front instead of waiting 20 years to get it a little bit at a time? This computation says you get $573,496, assuming a 6% discount rate. The state is actually using now about a 8.5% discount rate, which would mean you'd only get about $473,000. So in case 3, we're trying to figure out if we've got, let's say we're going to buy a house, right? We're going to buy a house, it's $400,000 house. We can get a 5% interest rate for 30 years. What's our payment going to be? So we're going to use a little different function. We're going to use the function called the payment function, equals PMT for, PMT for payment. We'll do Control A for our dialog box. It wants to know the rate. There that is. It's 5%. It wants to know the number of periods. It's 30. We don't know the payment. We know the present value is 400. And so the payment is going to be $26,000. Again, let me put the minus sign in there. We're going to pay $26,020 per year for 30 years. Now you can break that down by 12 months per year, but $26,000 a year, a little over $2,000 a month, would get us a $400,000 house on a 30-year mortgage. Now watch what happens if we go to a 15-year mortgage on this thing. And when we do a 15-year mortgage, we're paying a lot more, but our total interest is going to be a lot less. And I'm actually going to move this function down to this box here. And the reason why is I've got this set up for us so you can see our 5%, our 15 years, our present value. And so if we have, and I'll put that minus sign in there again. So if we did 30 years, we'd be paying $26,020 a year. That totals to, and that's not right, total payments. Wait a minute, that's not right. Hold on a second. So I had a slight error in my computation down here. So if we pay $26,020 a year for 30 years, that totals to $780,000. We buy a $400,000 house, we're going to end up paying $780,000 total payments. That $380,000 of that is interest, right? So $400,000 house, we're going to, over the course of a 30-year mortgage, we're going to pay almost $380,000 just in interest, almost the same amount we paid for the house. But if we do it over a 15-year mortgage, if we can swing a 15-year mortgage, we'll pay more per year, but watch what happens to our interest. We'll pay more per year. We'll pay $38,000 per year for 15 years instead of $26,000 for 30 years. But look at this. We only pay a total of $578,000, which is $200,000 less than earlier, which is $200,000 less in interest. It's all in interest. We save $200,000 if you can go with a 15-year mortgage as opposed to a 30-year mortgage. So let's look at this case 4. In case 4, we're going to have $1 million in the future. This is a bond. So we bought a bond. We bought a bond for $1 million, or we're going to buy a bond. And at the end of 5 years, we're going to get $1 million. In addition, we're going to get 5.5% every year during that 5-year period. So how do we figure the value of the bond? This one's kind of interesting. We're going to modify our equation just a little bit. We're going to do present value. We're trying to find the value of this bond. So again, the interest rate is pretty much the same. The interest rate is going to be 5%. That's the market rate. We know that the number of periods is 5. Now the payment is going to be it's $1 million, which is the face value, times the interest rate, which is 5.5%. And the future value is $1 million. So when we put all that together, it tells us that that bond right today would sell for $978,000. Actually, $978,938 is what it would sell for on the market. It's going to have a discount of about $21,000 on that bond because the market rate out there available today is higher than the coupon rate that this bond is going to be paying. Now, if this was more like 6%, it's going to sell for exactly $1 million. Whoops, 6% is going to sell for $1 million. If, however, this was 6.25%, it's going to sell for a premium of $10,530. So you can see how that works. Now, in the last one, case 5, we've got $160,000 in the future, 4.5%. And it's going to be there for 18 years. So let's say you've had a baby. You've estimated it's going to cost $40,000 a year to send this kid to college. You want to have that money available so that when the kid gets ready to go to college, they're going to have it. So your future value is $160,000, which will be $40,000 a year. And you know you can grow your money 4.5%. You're going to have the kid's going to be 18 when they start college. So how much do we have to put away today in order to get that. Now, we can do it two ways. We could figure out, okay, what's our present value? What do we have to put away in a lump sum today to get this? And I'm going to remember to put in my minus symbol finally. And our interest rate is going to be 4.5%. Our number of periods is 18. Our future value is 160. If we okay, it tells us that we need to put $72,448 away right now. But that's kind of hard to do. What if we put away some every year? Well, that's where we can use the payment function. We're going to do payment. And we're going to do the same information. We've got our rate. Our number of periods is 18. Our payment, our present value, we do know the future value is 160. So what's the payment? Well, if we could do about $6,000 a year, which is about $500 a month for the child's life, there will be $160,000 sitting there for that child's education when they get ready to go to college. So those are just some ways we might use the present value function. Finally, I want to take a look at the net present value. So net present value is kind of an interesting tool. The problem with this future value or present value is that, particularly present value of annuity, we're assuming that the payment is going to be the same each period. So if we go back to the present value and if we get out this payment question, we did future value, but we assumed the payment is going to be $12,000 every single period. But what if it's not going to be that? So first, let's just assume we've sold an item for 10%. The current rate of interest is 5%. The person's going to give us $1,000 down right now and $2,700 a year for the next 4 years. So that actually totals to, if we add this up, it's going to total, oops, I'll get it in a minute, to $11,800. It looks like a good deal for us. We're selling item for $10,000, we're going to get $11,800. But is that true? What's the present value of this stream of payments? Well, we can do that. We can say equals, and we're going to take this 1,000. We're going to add. Well, actually, I'm going to subtract the present value amount, because remember, present value would be negative. So I'm going to subtract the present value of my interest rate, which is 5%, my number of periods, which is 4, my payment amount, which is $2,700, and I get $10,000. So the present value of this is $10,000. It's a good deal, but not a great deal for us, right? If this guy had said, well, let me give you $1,000 plus I'll give you $2,500 each year. Well, in fact, is that as good a deal? I don't know, because if I go up here and change this, now I'm only got $9,865 as the present value. So I'd be better off making him pay up front. If I let him pay over time, I'm going to lose money because of the time value of money. The present value of that is less than the current selling price. Now, another way to do that is just to use the net present value function. So we'll do equals NPV. Now, this is actually going to give us, the net present value function actually gives us a positive value, which is kind of weird, right? Because the present value gives us a negative value. But we're going to go in here, we're going to put in that our interest rate is 5%. Now, what we're going to put in for our net present value is, or for our values, is we're going to highlight these payments. And I can do that, or I can put individual payments in, but I'm going to put those in like that. And now what I'm going to do is I'm going to take this formula. I'll hit OK, but that's not finished because I have to add the $1,000 upfront payment, right? So that's $9,864.88, just pretty much like that one. If I did my decimal points, there it is. So net present value does this, but what's nice about net present value is I can choose different payments. Maybe this guy's going to pay me $6,000 now, and $5,000 in year 2, and maybe nothing in year 3 and year 4. Oh, see, I get a different answer, right? Maybe the guy's going to pay me $5,000 in year 1 and year 2, and $1,000 up front. I still come out ahead on the deal. What if they're going to pay us $2,000 in year 1, maybe $3,000 in year 2, let's say $4,000 in year 3, and finally another $1,000 in year 4? well, I'm losing that. That's not going to work. He's going to have to pay me in year 4. He's going to have to pay me, let's say, $1,500. Puts me ahead. So if he pays me $1,500 in year 4, I'm ahead. But then again, I've got the risk. Am I willing to take this risk, and so that I get these payments? Because the present value of these payments, which are not all the same, right, is actually $10,315.25. And I can do this with net present value because I can't do it with future value because these payments aren't all the same. So the future value function doesn't work, but the net present value function does work in this case. So hopefully that was helpful. If it was, we'd love to have you subscribe to the channel. But remember, future value, present value, payment, and net present value are all financial functions that are built into Excel. We'll see you real soon.